This is a picture of my 6-year-old nephew Taherian and I at Omaha Beach during the past summer holidays. The day that he was born was probably one of the most memorable times of my life, igniting feelings and emotions that I didn't even know existed, and has taught me about the duality of love, where something that can bring you such blissful joy can simultaneously cause the most unbearable pain. You can tell a lot about us through this picture. We're ridiculously cute. We've just had an awesome swim. We're happy and cheeky. He trusts me as he's letting me bury him in the sand. But what you can't tell from this image is that Taherian is dying. He has a cancerous, incurable tumour growing in his brainstem called diffuse intrinsic pontine glioma. A killer that strikes at random at the heart of childhood, with an average prognosis of 9 months and a survival rate of 0. In Taherian's final months with us, at a time where he will be most vulnerable and his needs most dire, he will have no ability to communicate as the cancer disconnects the messages from his brain to his body. A conscious mind trapped inside a no longer functioning body. This lack of ability to communicate and interact with the world is shared by millions of people who live with severe physical disabilities due to injury or illness from birth or later on in their lives. The difficulties these individuals face are sometimes unfathomable, from severe health complications to a lack of access to education, meaningful employment, or community participation. But as designers and developers of technology, we can directly affect their quality of life and whether they're included or excluded from society. Technology has revolutionized our lives, from the ability to restore our vision through putting on a pair of glasses, to sending emails, to using touchscreens on our phones. Where would we be without them? But what you probably didn't realize, is that all of these examples were initially designed as assistive equipment and technologies to help people with disabilities, constructed through universal design principles that ensure products, services, and environments are usable by everyone to the greatest extent possible. There are a number of existing technologies that are designed to enable people with profound disabilities to interact with the world around them, but all require some form of reliable physical input, which is not always possible. So what we really need is the ultimate universal access tool, something that enables us to go directly to the source of communication, our brain. 5 years ago, a few friends and I formed a company named ThoughtWired with the aim of creating technology that uses the power of thought alone to communicate. Today, I'd like to talk to you about our initial journey and approach to researching and developing this new technology, and hopefully motivate you to think differently about your designs and design processes. Brain-computer interfaces, which I'll refer to as BCIs for short, are unlike any other interface technology that we've ever seen or thought was possible. The basic premise of this technology is to observe our brain activity, interpret patterns of activity using machine learning and pattern recognition algorithms, and turn these into control signals to allow a person to communicate and interact through a computer. The human brain remains the most enigmatic organ in the body. It's made up of 100 billion nerve cells called neurons, and each neuron has the ability to communicate with thousands of others to regulate our physical and mental processes. The way that they communicate is through electrical signals or exchange of chemicals called neurotransmitters. This process causes an increase in oxygen and blood flow in areas of the brain where the neurons are highly active. With today's technological advances, we can observe the electrical, chemical, and blood flow changes in the brain as it processes information and reacts to stimuli that are picked up by our senses. From these observations, we can produce images of the brain's structure and activity to understand specific cognitive processes that are happening at a given time. So how do we make these observations? We can use invasive methods by surgically implanting sensors on the surface of the brain or within it, or non-invasively using different brain imaging techniques and optics that measure blood and oxygen flow, or sensors that measure the electrical signals and changes to the magnetic field using surface mount electrodes. Electroencephalography, or EEG for short, measures the electrical signals produced by the brain activity from electrodes placed on the surface of the scalp, like this image here. This technology was developed in the early 1900s, so it's been around for a while, invented by a German psychiatrist named Hans Berger, who interestingly actually wanted to measure the physiological basis of psychic energy, specifically telepathic communication. He couldn't quite prove the existence of telepathy, but he did provide the first evidence of the brain's electrophysiological processes. So depending on our level of consciousness, the actions that we're performing, and our thoughts, our brain activity shows different rhythmic waves in different areas of the brain. EEG is the most used method to measure brain activity for BCIs, as it has the highest temporal resolution, making it most applicable for computer interaction. The technology is also very portable. It's easiest to set up and cheaper to engineer than all other options. When ThoughtWired first came together, one of the first things we did was to look at what's been done with BCI technology and what's available for people with disabilities. We found that there were a handful of commercially available BCI hardware systems, but these lacked the other components to make it into a usable form of access interface for people with disabilities. Instead, they had been marketed as alternative game controllers. We also found that the underlying technology wasn't even that new. It's been heavily researched in academia for over 50 years. And yet no one was using this technology as an assistive solution to help people with disabilities. So, what is it that's holding this technology back from becoming a real-world solution? We found that it's actually the approach taken during the research and development of the technology. So problem solving is an inherently difficult task to do well, and researchers often adopt what's called a reductionist approach to finding solutions. This means that the problems are broken down into their smallest parts and studied in relative isolation. Even though this makes it much easier to tackle complex questions, dividing what we know into categories creates boundaries between different disciplines. In the technical sciences, like engineering, where BCIs have been studied the most, they try to understand the hardware and software components in isolation from the actual users of the technology. Unfortunately, this has caused a misunderstanding in the human needs, the characteristics, capabilities, and desires of the people these systems will benefit the most. 90% of the research on BCIs to date have excluded research with individuals who have disabilities. They're mostly conducted in extremely controlled environments of research labs and clinical settings, where the technology is only trialled once, giving a very narrow and flawed understanding of the long-term usability. So why aren't more people with disabilities engaged in the research and development process? Sadly, it comes down to the difficulties in working with them. Some of these difficulties are the smaller number of people with disabilities who can participate due to their complex needs and health conditions. They're difficult to locate and recruit. They require assistance and supervision by carers, and they often can't travel, or if they do, they require an alternative means of transport, which isn't readily available, so it can be a logistical nightmare. They're also a very heterogeneous group, making it hard to generalise results, and they also require strict ethical approval. For us, this wasn't really good enough. So we decided to do our own in-depth research. We didn't have a means, because we were a startup, we didn't have much funding. So I went back to university and enrolled into a PhD program at the University of Auckland to challenge the way that the existing research is conducted, trying to bridge the fields of psychology and engineering to move BCIs out of limbo within clinical and research settings and into the real world. For this, we used an integrated approach that weaves the needs of users and the context of use into the research and development process. And there were times where I felt like jumping off that bridge. The user-centred design methodology presented us with the framework to enable the future users of BCIs to influence its design. In our scenario, our users were separated into 3 categories. Our primary users, who were people with severe physical disabilities but minimal cognitive impairments. Our secondary users encompassed family members and carers who would be required to set up and update the system. And tertiary users consisted of clinicians, therapists, healthcare providers, and special education teachers who will be affected by the use of the product and make decisions about its usefulness in order to fund and purchase it. Most of you guys are aware of this process, but for those who aren't, I'll go over it. A typical user design process is iterative, where emphasis is placed on understanding the user needs and the context of use of a potential solution. So once we understand this context of use, the iterative process follows 3 stages until a user-adapted product comes into fruition. Firstly, the user requirements are specified. Secondly, design solutions are produced to meet these requirements. And lastly, the designs are evaluated against these requirements. So our first step was to develop an understanding of assistive technology in New Zealand. To achieve this, we held a number of focus groups that looked at the perception of assistive technology held by all of our user groups. Because many of our participants were non-verbal and a usual exploratory discussion was difficult, we briefed them on our questions beforehand. Some of our participants had no means of communication, so their family members served as proxies to what they may have experienced. We also conducted ethnographic research where we observed the day-to-day of all of our user groups, and I became a caregiver to gain first-hand experience and develop authentic empathy and compassion. We spent a good year truly embedding ourselves within the community and building relationships as we needed ongoing commitment with our user groups. This contextual research painted a grim picture of our assistive technology sector. We learned that up to 75% of assistive technologies are abandoned. This is due to the poor assessment process where the needs of different stakeholders weren't considered. And the actual assessment process was lengthy, where people had to wait on average 2 years before they gained a tool to help improve their lives. So by the time they received the technology, it was no longer a suitable solution. There's also a lack of technical support and training for our users. And most importantly, they felt that there was little consideration of their needs through the initial development of these assistive systems. Many families were burdened and stressed by the daily pressures of care for their loved ones. They adapt their environment and create coded methods of communication that to us seemed almost telepathic. This meant that more often than not, the introduction of a new piece of technology was more of a hassle than a liberation. In schools and residential settings, teachers and carers were so flustered with their workload that setting up and monitoring clunky and perceivably complex technology only added to their stress. So instead, they would resort to low-tech options, such as cards that had symbols representing a yes or no response. Sadly, these negative perceptions of assistive technology only served to isolate the disabled individual even more. Our next step was to understand the user requirements. Our original focus group had incorporated a workshop element that aimed to understand what these user requirements would be for a BCI. However, because BCIs are so unique, none of our participants could really envision something that didn't exist in their world. Before a new experience exists, people usually use concrete operational thinking rather than imagine the hypothetical or abstract. And also, because of the physical limitations of our primary users, the normal prototyping and creative tasks involved in design thinking were not possible. We had to gain an understanding through an actual interactive process. So in a sense, we had to jump to step number 3 and produce a hypothetical BCI solution before we could understand what the user requirements could be. We prototyped a BCI experience, this is Ross by the way, using a commercially available headset that came with its own machine learning algorithms that calibrated the control inputs with a user's thought patterns. We built some basic software that enabled people to use these calibrated thought patterns to switch on a light, play a puzzle game, and access a media player. This awakened new ways of thinking for our users, enabling them to explore the potentials and limitations of BCIs. This first prototype was tested with individuals who have spastic quadriplegic cerebral palsy, a disorder that's caused by injury to the motor areas of the fetal or developing infant brain and causes essentially locked-in syndrome. Due to their complex needs, their carers, therapists, and teachers were also present throughout our trials. So we would visit our users 3 times per week over the space of a month, where we tested the feasibility of the technology, including the hardware, software, and training components. Initially, we incorporated quantitative usability and psychometric questionnaires, but these were too difficult to implement and adapt for our primary users. At the end of the trials, we interviewed the secondary and tertiary users to gain an in-depth understanding of what their user requirements would be, but they also served as proxies to our participants who didn't have a means to effectively communicate. So what did we learn? In a nutshell, our prototype was almost impossible to use. In fact, only one person could effectively use it. The hardware that we employed couldn't be used by our primary users as they weren't compatible with their head and neck rests, which they required to keep their heads up. Having multiple sensors dispersed throughout the scalp, it was really uncomfortable and took about 20 minutes to set up. It often moved, causing signal loss so people couldn't use the system. And most importantly, it didn't look cool. So it needed to resemble mainstream technology. It had to be comfortable to wear for long periods of time, and we had to remove all components from the back and the sides of the device. Our training software was heavily visual-based, whereas many of our users had some form of vision impairment. We needed to explore multimodal feedback. Our training structure was unmotivating and cognitively tiring. Users wanted better games and to access more useful applications. The usual rigorous, controlled, and repeatable scientific approach to conducting trials was also impossible. All of our primary users had different symptoms, needs, and adaptations. They had severe and complex comorbid health conditions, which meant we weren't able to test them consistently at a given time, on a given day, and our sessions varied in duration based on how they were feeling. And finally, our users told us that it wasn't just the technology that needed to be addressed, but we needed to innovate around the funding and assessment procedures to ensure that people could gain access to our technology faster. We had to look at the bigger picture to achieve more immediate impact. This research showed us that the usability of a given design is not just an attribute of the device, but is the outcome of the human-device-environment interaction. And placing our end users at the heart enabled us to uncover the multitude of facets that may build barriers to the adoption of our technology. As a result of multiple evaluations through trialling reiterations of our system over time in the real world, we now have our nth prototype, a sleek version of its predecessors, which you have the opportunity to play with during the workshop period. And when you're using it, I'd like you to think about how it might feel to have to use a BCI in your everyday interactions. So we've proven that the technology works, and we've distilled all the challenges that we need to solve for. And at the heart of this is ensuring that we remain universal. And although it still needs to evolve from this research prototype into a market-ready product, the underlying architecture means that our system will be completely customizable based on a user's needs and extensible to allow for other emerging access interfaces and software applications. When I first started working on this project, I realized I had never really interacted with people who live with severe and complex disabilities. This realization was quite jarring. I wondered if I was subconsciously discriminating against people with disabilities. But then I looked around me, and you can see it even in this room. I wasn't discriminating. The reason is because people with disabilities find it very difficult, if not impossible, to live in the world that we've designed. A society that systematically excludes the largest minority group on the planet. 1.3 billion people live with some form of disability, and that number is going to increase with the aging baby boomer generation. Most of the facets of life, from the design of our built environment to digital services and physical products, these are designed with only the perspective of the average user in mind. Each place, each interaction, sacrifices the humanity of billions of people and opposes their dignity in different ways. How our current culture defines, thinks, and treats people who have disabilities is how future citizens may be perceived if and when people who are able-bodied become less abled by age, injury, or disease. But we can achieve access for all if we look at everything through the lens of universal design. As designers and innovators, we have the power of knowledge, drive, and passion to directly make a change, bringing to life products, services, and policies that will uphold people's dignity and human rights. The creative realm in which we operate is an enormous privilege, and with it comes an even bigger responsibility. Because when we design for the fringes, we're likely to satisfy the masses. By truly empathizing with others, we create things that are out of this world. Actual, innovative, world-changing creations. And we know this to be true when we look at the most revolutionary technologies of our time, from the typewriter to the telephone to the personal computer. All of these technologies were designed for niche markets. Over the ditch, the National Disability Insurance Agency has developed an artificially intelligent virtual assistant named Nadia. Nadia was co-designed with the disability community as a result of strong calls for information to be more accessible and personalized. Instead of making sense of jargon and navigating through confusing websites, you simply have a conversation with Nadia. Now imagine how disruptive this type of interaction will be for the way that we may surf the web in the near future. And this is exactly the thinking that we have behind our product, in that yes, we are first and foremost designing an assistive solution, but it's also the ultimate universal access tool, as its only requirement for usability is a functioning mind. I can't save my nephew's life, nor can I restore normal physical function in the millions of people who live with a severe physical impairment. But what we can do as a collective is ensure equal access to opportunities that will improve their quality of life, no matter how short or how impacted it is by disability. So when you go back to work next week and when you start your next project, I ask you to wear your universal design hat. When you're out and about doing your day-to-day, I ask you to wear your universal design hat. Be more conscious of the little details and logistics that you've been conditioned to overlook. How would someone with a vision, hearing, memory, or physical impairment interact with your design? Together, let's create a future that removes this dichotomy of abled versus disabled and instead embraces the full spectrum of human diversity. Thank you.